I'm enjoying the conference very much. So I understand that I'm the last talk of the day and the only thing between you and your banquet. So I will try not to go overtime like I did yesterday. I promise. So today I'm going to talk about some applications of some of the things that I talked about yesterday, specifically digital signatures for network coding. And let me first say that this is joint work with two of my colleagues from Microsoft Research, Dennis Charles and Kamal Jain. And this is actually a good example of, although I couldn't understand everything that was being said in the previous talk, I understood from the slides that there was some kind of advertisement for the role of mathematicians in cryptography. And this is also such an example or an advertisement. Kamal Jain is a colleague of mine who is working on network coding, and he came to us with the problem of essentially basically needing kind of a homomorphic signature scheme, which is what we came up with based on the elliptic curves and pairings that we knew about. So that's what I'm going to explain to you today, is kind of a solution that we came up with based on the mathematics that we know. So first I'd like to describe what network coding is. So the setting here, the application you should think of is content distribution or even content storage, it could be. But let's think about content distribution where you have a single source of the content. Let's say Microsoft is trying to distribute updates for its software, or some content producer in the movie industry is trying to distribute a movie or something like that. So a single source of content, but many, many potential recipients. And the question is, how can you most efficiently distribute your content to all of these recipients? So I wasn't so good with PowerPoint in making a diagram or a drawing, so I wanted to actually draw it on the board here to give you a better idea. So suppose your S is your source of the content. This can be considered as a particular node. And then there's a lot of recipients. So typically your network of peers, these are all called peers in our content distribution system, could have the potential of also communicating with each other, in which case we obtain what we call a peer-to-peer content distribution system. So there could be lots of other peers here, and the peers distribute content to each other. So, and then eventually you very quickly come to the situation where there are peers who are receiving content from more than one other peer. And then it's not necessarily directed all in this direction. It could be an undirected graph, or it could have loops in it, things like that. So a priori, we don't know really anything about the topology of the peer-to-peer content distribution network. There could be many different shapes of this network. But one thing that we know is that if the source just divides up their content into a bunch of blocks and then just distributes pieces block by block to the network, one thing that happens is that it could be the case that it takes a long time until all of the nodes, all of the peers have received all of the blocks. Just because of the patterns of distributions, you could get one of the blocks that went over here somewhere into the network, and then it took a long time until it got back over here to some other part of the network. So this is the basic problem that network coding made a big improvement on. So I'm going to tell you the network coding model in the language of graphs. So I'm going to let G be a graph where V is the set of vertices. So these are the peers in our network. And E are the edges between the peers that exist. The V represent the peers in the system. And the source S is the one transmitting the content to some set of the peers. And the file to be transmitted is broken up into blocks of equal length. So it could be a very, very long file. But what you do is, in this case, we're going to encode it as vectors in FP. P, a finite field of P elements, and there's going to be K vectors, each of length D. So K and D are very important in this scheme here. You'll see in the linear algebra in the next few slides. So K is the number of chunks that the file has been broken up to, and D is the length of each chunk. Okay, so what network coding does, network coding was introduced by a number of different authors, including Elsewhere, Tsai, Li, and Young, and Chu, Jane, and Wu, and later improved by Gonzalez and Rodriguez. So the idea that they had is that instead of just dividing the file up into chunks and sending individual chunks to different peers, what you should do is you should take the chunks and you should make linear combinations of them. And then every time when you receive a linear combination, if you're a peer, then you should actually take all the linear combinations that you receive and you should recombine them so that you have this very fast mixing of the packets. And that way, every time you receive a new chunk from a new peer, you're very likely to have new information in that chunk because it's very likely to be linearly independent from previous pieces of information you've used. So the way that they do this is to, now what we're going to do is we're going to write down, so each vector is, the vectors which were the chunks of the content are written here. And remember there were K of them, so you can think of there being like K rows in this matrix. And then the first K bits here are just used to tell which chunk are you looking at. So here, if you have the ith vector out of the K vectors, the ith chunk, you put a 1 in the ith column. So these vectors encode not just the chunk of the file, but also a tag or a linear information that tells you which chunk do you have. So then if you receive the chunk V1 and the chunk V2, then you can combine them and you put V1 plus V2, and what you'll have is the two vectors W1 and W2 added together, but then in this area here, you'll see a 1, 1, and then 0 zeros everywhere. So it tells you both the linear combination and which linear combination are you supposed to have. Okay, so, and this gives you a vector of length K plus D in FP. Okay, so this is the process of recombining of the vectors. I realize this notation was a little bit confusing, so let me just say what the Y of E is supposed to be. The Y of E is any linear combination, call it AIs, of the VIs. So if you're a peer here, you receive a Y of E, like say this is E1, and this is E2, you receive Y of E1 and Y of E2, and then you recombine them with your own scalar multiples that you pick. These are your scalar multiples. And you recombine them and you send out, you have a new combination that you now send out to someone else. So that's the notation that I'm using here. And so you continue to recombine these packets. And you get very fast throughput, but so what do you do if you're a peer now and you've received a lot of these packets and now you want to reconstruct the file that you've received? Well, that's very easy now. That can be done via linear algebra. So you've received a bunch of vectors like this. These are combinations of the vectors, and these tell you which combination it is. So to find the original file, the W1 up to WK that you need, all you need to do is to solve this linear algebra system for the WIs. So you know the GIs, the GIJs, and the UIJs. And so you just need to invert this matrix and multiply, and you'll have your content that you wanted to get. Okay, so what is the problem with network coding? The main issue is that it's even more susceptible to pollution attacks than the previous version of peer-to-peer content distribution would have been. Before you started using network coding, peers were distributing content to each other, and if someone chose to send you one chunk of the file which was corrupted or polluted, then that would really only affect that particular chunk of the file. And if you figured out that that user was malicious, you could throw out that chunk or refuse to receive packets from them in the future. The problem with network coding is that one malicious node will quickly pollute the entire network, because what they're doing is they're recombining, they're actually, let's say they're just injecting garbage into the network. But you receive some garbage and then you recombine it with all the good packets that you got from others, and you send that out, and now the packet that you sent is corrupted. And quickly you'll have the effect that every node which received a packet coming from this polluted packet in any time in the past will be completely useless. It infects the entire distribution system. So it's particularly important to address this problem of pollution attacks. So one way to try to do that is to try to provide authentication also of the packets using digital signatures. So this is just an explanation about the value of network coding, which I explained already. But the impact of pollution attacks is even greater here. Okay, so let me describe the signatures. Well, first I'll just tell you one anecdote before I describe this signature scheme. At the time when we were working on this, around 2004, was actually a time, I don't know if you've heard of BitTorrent. BitTorrent distributes content using peer-to-peer systems. And a lot of users were downloading episodes from a television station, HBO, in the United States. They were downloading episodes of Rome, I believe, was a TV show at the time. And BitTorrent was being used to distribute this content essentially illegally over the internet, yes. But HBO didn't like this because they were taking their content and distributing it illegally. So they just started injecting garbage into their network, and they just ruined the distribution system there. But that was at the time when we still weren't really sure whether peer-to-peer content distribution networks could be actually useful in a legitimate commercial setting. There, BitTorrent was being caught in an illegitimate commercial setting where they were distributing content that should not have been distributed. But today, I think everyone believes in the actual legitimate uses for peer-to-peer content distribution systems for commercial purposes. So for that reason, it's even more important that we solve these problems of authentication of packets. Okay, so now let's turn to elliptic curves and elliptic curve cryptography and pairing-based cryptography and how they can contribute a solution in this context. So let E be an elliptic curve over a finite field FQ. What we need here is we need to take a bunch of points, R1 up to RK and P1 up to PD, the same K and D from before, on an elliptic curve over FQ, but these points need to be P-torsion points. That means that if you multiply them by P, they're equal to 0. So one way to do this is to just construct an elliptic curve E over a field FQ such that the order of the group is actually P, because then every point is a P-torsion point. So in the example in the end, I'll show you how we can do this, how we can construct a curve with with order P, where P is a prime. Okay, so now what we're going to do is we're going to define a hash function, which goes, this is not the usual hash function oftentimes for elliptic curve-based protocols, you need to take a message or some bit string and you need to turn it into a point on the curve so it can be used to, for example, for a signature. I think I gave the example yesterday of the Bonin-Lin-Shackham signature scheme. And there we had a hash function which I called H, and that took a message that was going to be sent, and in order to provide the signature, it converted the message into a point on the elliptic curve, and then the signature was a multiple of that point on the elliptic curve. Well, this is analogous, but this is a different hash function, okay? This is a very kind of, let's say, kind of homomorphic hash function. Because what it does is it takes a vector here in fp to the k plus d, and it converts it into a point on the curve by taking multiples of the given points. So these points ri and pj are given, and so you just take these multiples, the ui multiples. And in that way, the important thing to notice here is it preserves the homomorphic structure from here to here. This is a group, it's a vector space over fp, but it's also a group. But it's a group in which every element is killed by p, right? If you multiply a vector by p, each one of the components will be killed by p. So it's very important that this hash function be a homomorphic hash function. Now, this isn't probably the only way to do this, to construct such a hash function, but this is the way that we chose. So the next step is to describe how to sign a vector. So in the previous slide, I was showing you just a hash function, how to convert a vector into a point on an elliptic curve. This is going to be for the purpose of doing the signature, much like the Bonin-Lin-Shackham scheme that I showed you yesterday. But remember, these are the vectors that actually need to be transmitted and recombined by the peers. So these are the vectors where you're going to be doing the linear algebra and the linear combinations. And the reason for this function to be a homomorphic hash function is that we want to have signatures of these vectors. The signatures are going to take place on the elliptic curve, but we want combinations of valid vectors to be able to give you signatures which are valid signatures as well. Okay, so how do you sign a packet? Remember, the model is here that the source is distributing the content. And no one in the network is supposed to have the power to alter the content. They're only supposed to receive content, do legitimate recombination, and send it on to other peers. So really, only the source is supposed to have the power to sign. If anybody else had the signing power, the signing secret, then it would allow them to send packets which look like they're authentic when they're not. And that's what we're trying to prevent. So we're going to assume that the source has a secret key, which we're going to call, these are all secret keys, S1 up to SK and R1 up to RD. And only the source has these secret keys. So what's going to happen is that a vector is signed by computing its image under this hash function, but now they're going to use their secret to produce points on the elliptic curve which are unknown to others that don't have the secret. And this is the discrete log problem. Someone else who just knows S1 times R1 doesn't know what S1 is, even though they know what R1 is. Okay, and then in order to enable the verification of these packets, the source also publishes these other public keys that go along with the public keys R1 up to RK and P1 up to PK. So this will be the signature of a vector, and it can only be produced by the source having the secret key. And so the only condition on these points is that the pairing of these points, the RIs and the PIs, the pairing of those points with Q should not be equal to 1. So if you know very much about the way the pairing works on elliptic curves, in general, for an elliptic curve over a finite field, that's, at least if it's not super singular, the M torsion looks like Z mod MZ cross Z mod MZ. And in this case, let's call it Z mod PZ cross Z mod PZ, because we have a group of order P that we're working in. And so essentially what you're going to need in practice is that this Q needs to be in the other, it needs to be linearly independent from these points PI and RI. So it needs to be in the other piece of the P torsion. And typically, if your curve is not, doesn't have all of its P torsion defined over the base field, typically what will happen is you'll have to pass to an extension of the finite field in order to get a point which is another P torsion point which is linearly independent from the ones in the base field. So you'll see why this is important when I give the example in the end of it affects the construction. So in many typical pairing constructions that you may have seen, this Q would be defined over an extension field because you need to have this property. But you can also make it so that it can be defined over the base field. Okay, so now what I've described so far is the source can sign the vectors, and now the point is that these signatures, because they have this homomorphic property, these signatures, when you receive a valid signature and check it, then you can recombine it with other valid signatures going along with all the packets you've received, and you'll be able to send out a new signature on your recombined packets that will also be valid, but without you having the secret signing key. So the way this works is, this is the same notation from before. If you are going to form a combination of these packets in this manner, then what you need to do is you need to take the signatures that you receive for each of these vectors, and you need to recombine them in the same way, and this will be a valid signature on this. So then whenever you are a peer that is receiving a new vector, you need to check the signature. How can you check it knowing only the public information? Well, the way you check it is you take the vector that you received. Now, all of these points, the PI, PJs, and the SJQs and the RJQs, these are all public. And the U's and the V's you also know because that's what you received. And here's the signatures. So this is these are all pairings that you can compute. Actually, one thing that's interesting to note here is that you have to compute basically K plus D plus 1 pairings here. So this is important from a computational or a practical point of view, that you need to be able to do the pairings fast enough so that this is not a bottleneck. This should not be something that's computationally infeasible for peers to perform peers in your network. Okay, so I guess that really completes the description of the scheme. The overview is that the source signs the packets, peers receive signatures, they can recombine them and send out valid signatures on the recombined packets. And so it prevents pollution attacks in the sense that every time you receive a packet, you can check its signature before you recombine. If you are looking for something more efficient to do, you can actually do batch verification of these signatures. That is, you can take a whole bunch of signatures that you receive from all the peers, and you can check the signature with one computation of the form that I described here. And if it doesn't succeed, then you can do kind of a a tree algorithm to try to figure out which was the bad signature. But that's one efficient thing that you can do in this scheme, is batch verification of signatures as well. So now the next question is, so why is this secure? So basically, I've showed you something that looks like it's kind of based on this, just essentially the discrete log problem. And the theorem that we showed in our paper is that indeed it is based on the discrete log problem, in the sense that finding a collision of the hash function h is polynomial time equivalent to computing the discrete log on the elliptic curve E. And then that also leads to the fact that forging signatures is as hard as the computational Diffie-Hellman problem on the elliptic curve E. So this is something that was actually essentially known beforehand, but kind of in a different, it was described in a different way. So overall, the scheme it can be adapted actually to be used for other purposes as well. So let me just point out a couple of the aspects, design aspects for implementing this scheme. So the fact that it's pairing based, as you can see from what I said yesterday, may mean that the computational overhead could be fairly high. So there are, I should probably point out that there are other approaches to adding signatures to network coding which are less computationally intensive. So actually the reference I gave in the beginning to Gidantis and Rodriguez was using a kind of a homomorphic hashing that didn't have the same kind of security guarantees, is much more efficient than the scheme that we're talking about here. And there have also been, since this work, there have been subsequent proposals which are based on other things that are possibly also more efficient. Okay, so these days, as I mentioned yesterday, we like to work with at least a 256-bit prime field. Depending on the security level you're looking for, you might be willing to use something like a 160-bit prime field, which is the example I'm going to give you. We have a kind of an easy setup of the system with a field which is of size roughly p squared. This is an artifact of the kind of simple construction that we used to create a pairing-friendly curve here. You could do better than that. You could actually, for elliptic curves, you can use pairing-friendly constructions where the ratio of the field size to the group size is more like 1 instead of the ratio of the logarithms being more like 2. So this is rather unfavorable in the sense that you're losing efficiency by taking a field size that's twice as big as it needs to be here. So I guess also compared to, for example, the homomorphic hashing scheme of Gidantis and Rodriguez, our scheme has an advantage in the sense that it actually provides authentication. The communication overhead per vector is overhead, I'm talking about the signatures here, is 2 elements of FP, the x and y coordinates of an elliptic curve point, which is 512 bits for a 256-bit field. Oh, I'm sorry, yeah. This is actually, this should be FQ, I believe, so this would be twice as much. But one thing that you can do is you can use some kind of point compression so that you send only the x coordinate and at most a couple of extra bits of y to tell you which y coordinate you should use. So we can, this is kind of optimal point compression here where you use only 1 bit of y. So the computation of the signature, as you can see from the description, is, so let me see, where's the signature? You're just doing combinations of the signatures that you had to perform on each one of the packets that you received. Oh, sorry, here. So these signatures just require you to compute this hash function. So the total computation time for a signature at each edge is roughly just proportional to the in degree of the vertex in the graph. The verification, however, this is what takes more time. So that's why I was suggesting that you could do perhaps batch verification of signatures, something like this. So there's a constant hidden here which I haven't made explicit, but as you could see from the algorithm that I showed you yesterday, that you can compute pairings in something like log q squared operations, and you need to do roughly d plus k of these pairings. So that's where this computation time comes from. So just to give you an idea, the timings I'm going to show you at the end, using the basic tape pairing, you can do something like 100 pairing computations per second, which is not very much, actually, in my opinion. 100 pairing computations per second means that if you have a lot of pairing computations to do, that can be a significant overhead. And that's on a regular desktop computer, like I don't know, forget, 3 gigahertz or something. So if you were doing this on a small device, that could be even more significant. Okay, so now let me move on to the question. This is the question that's more of mathematical interest to number theorists, for example. So how do you actually construct such a curve that has, let's say, prime order P over a field FQ, which also has the property that the embedding degree is small enough so that your pairing takes values in a small enough finite field to be reasonable. So I'm actually going to give you an example of pairing degree 2 here, and that actually can influence the size of the field that you want to take. But so let's fix a large prime P, and I apologize, but I, for some unknown reason, switched notation here. In the rest of this talk, L was Q. L was what I was calling Q. Now L is the prime that was supposed to play the role of Q in the previous slides. So what we need is a prime field FL and an elliptic curve over that prime field such that several things need to be true. So you need to have a group of order P lying in the rational points on the elliptic curve over FL. So if you take the number of points on the elliptic curve over the field FL, it's equal to L plus 1 minus the trace of Frobenius, T, which is some integer which has size at most 2 square root of L. So P needs to divide this quantity so that you can have a group of P torsion, a subgroup of P torsion points. So here's another requirement. In order to actually construct a curve, an elliptic curve, over a field with a given order, this can be computationally a tremendously difficult task. I mean, we have algorithms to do it. We know how to do it. But they can be prohibitively large. The computation can be so large that you would not be able to perform it. So in order to make that task doable, to actually construct a curve with a known order, what you need is you need to be able to construct it with what's called complex multiplication, where the field of complex multiplication is very small. So the way you can ensure that is by this second condition here, which, if you notice, t squared minus 4L is actually going to be the discriminant of the field that the curve has complex multiplication by. And so what you need is that this discriminant should be some large square times some small value d. Okay, so actually I should have maybe put a little more detail. I'm going to write another line or two here to explain condition number 2. So the idea is that if you have an elliptic curve E over a field FL, it has what's called the Frobenius map. So it has a map pi from E to E, actually over the algebraic closure of FL. And this map just takes points, x comma y, to nth powers of points. So this is what the map is. But the map is known to satisfy a characteristic polynomial, which is, so pi squared minus t pi plus L equals 0, where t is this Frobenius that I mentioned, the trace of Frobenius. And what you can see from the quadratic formula is that since pi is an endomorphism that satisfies this polynomial, you can use actually just the plain old quadratic formula to see what field a solution to this equation should lie in. So the quadratic formula says that this basically pi is equal to t plus the square root of t squared minus 4L all over 2. So you can see that this is this discriminant here. This is actually a negative number because of the Hasse bound on t. T is no more than 2 square root L. So here what you have, and this is often called d or minus d if you want d to be positive. But in my notation, I'm calling it dy squared. That is because what I'd like to have is I'd like to have d be small and have it be multiplied by some large square here. Because you can see typically this value is going to be around the size of L. And if P has to divide something like, L is going to have to be basically of cryptographic size. So there's no way, if you just let D equal this quantity here, there's no way you could compute the Hilbert class polynomial, which is what you need to compute in order to use the complex multiplication method. Okay, so this condition here is so that you can actually construct the elliptic curve once you've found the parameters that you need. And then finally, so this third condition is that this is the number of points now over the quadratic extension. So this is the number of points on E over FL squared, and it's L squared plus 1 minus 2 times PT plus L. And this should contain all of the P torsion points. So what we want is that this should be congruent to, remember the P torsion of an elliptic curve is going to be, for a non-supersingular curve, it's going to be Z mod PZ cross Z mod PZ. So it has order P squared. So you want P squared to divide this group order. Otherwise, there's no way you can have all of the P torsion points in the degree 2 extension. Okay, so these three conditions need to be satisfied, and here is one easy way to get them to be satisfied. So if you set the trace equal to 2p, then that makes this condition here turns into the condition that L plus 1 should be congruent to 0 mod p. So if you insist that L is congruent to minus 1 mod p, then this will be satisfied. And if you look at condition 3, it's exactly that same condition that will make this satisfied for if t is set equal to 2p, then this part is already congruent to 0 mod p squared. And all you need is that if L is congruent to minus 1, then this will also be congruent to 0 mod p squared. So we're going to take a particularly small d. A very easy choice for d is minus 4. And you can see from this, if you set t equal to 2p, this just turns into the condition that y squared should be congruent to minus 1 mod p. So this is a very nice thing because what you can do is you can just look for, you find out what the square roots of -1 are mod p, and then you can just look for solutions to this equation here, such that L is prime and Y is congruent mod p to one of these square roots of -1. And then you're done. You will have found your parameters. The only parameters that you're really looking for, the only parameter you're really looking for here is L, because then T was equal to 2p already, and that tells you what your group order is of your elliptic curve. Okay, so I guess in the last part of my talk, what I want to do is just give you a couple of concrete examples and some timing results of what it takes to implement this system. Okay, so here what we did was we fixed a prime p, and this was about, I think, if I remember correctly, it was about 160, between 160 and 170 bits. So this is a bit lower security level, just because we're doing this a while ago before the minimum became something like 256. And so the L that we found using the method that I just described is given here. It's basically p squared plus y squared, where y was a value, y was a value that was prime, y was a value that was congruent to a square root of -1 mod p. Yeah, so I guess you can see L was supposed to be, yeah, you can see from this that if you divide this through by 4, L was supposed to be basically p squared plus y squared. So this value, this second value here is just y. That's y. Okay, so the nice thing about having chosen d equals -4 is that that corresponds to a field of complex multiplication which has class number 1. And the Hilbert class polynomial has degree equal to the class number. And so it's particularly easy to compute. And in fact, we actually know that curves of this form, for primes of the proper form, that curves of this form will be suitable. So, but you can check, for example, using magma, that the group order is suitable. It is what you think it should be. So you can check that it's 0 mod p, and this is pretty fast computation. And then you also need to check what the number of points is over the field of L squared elements, and you find that it is also 0 mod p, which was a necessary condition to have all of the p torsion over this field. So in fact, what we actually do is, to show that all the p torsion really is contained here, we generate a p torsion subgroup, 2 independent p torsion subgroups that generate the whole p torsion. So I'm sorry, this ran off the screen here. But this is a representation for these points. Now, these coordinates are in FL squared. So this U here that you see is an element that's generating the degree 2 extension of FL. FL squared is just being written as being generated by the element U modulo irreducible polynomial, quadratic irreducible polynomial. And then we actually compute what the Weil pairing is of these 2 points. So this is the Weil pairing, and here the Weil pairing is being written as an element of FL squared star. So in order to think of it as a group of roots of unity, you need to think of a subgroup of FL squared star. Okay, so finally, just to give an idea of the timing, how much computational effort it takes to compute pairings on such a curve. Thanks to Michael Narig, he's the author of one of the pairing-friendly families of elliptic curves, the Pareto-Narig curves, and he's currently an intern at Microsoft Research in my group. And so he very kindly generated some timings for these implementations. So if you take an elliptic curve over FP with P of size 256 bits, and here the embedding degree is 12, there's a C implementation by Peter Schwab for the European Union project for implementing pairings. And the performance was measured on Intel Core 2 quad, but using only one core and 2400 megahertz. And the measurements were averaged over 1,000 measurements per pairing. So here is the number of CPU cycles for the tape pairing. And so I probably should have put this up here, but I divided it out. And this is what I was telling you. This implementation can do about 100 pairings per second on this. So what you can see from these numbers is if you implement the generalized eta pairing or the 8 pairing or the optimal 8 pairing, you actually get better implementations, better to the extent this optimal 8 pairing is roughly half as much computation as the tape pairing. So that's a very significant improvement. So roughly speaking, you'd be able to do about 200 pairings per second using the optimal 8 pairing. So this gives you a lot of motivation for trying to improve pairing computations on elliptic curves. Okay, so I think I'd like to stop there. Thank you.